we have discussed about design of sprue, and then we did little bit of design on runner, and then we are discussing about different gating systems. Okay, so we had an introduction on top gating, and also it's known as vertical gating, and also we have seen that this top gating is used for non-ferrous material. Okay, so we can't use it for non-ferrous material. Why? Because it is having light density, and as the material is having light density, already we know that there is a chance of turbulence because of high velocity at the end of the sprue, and because of that, splashing of liquid metal might happen. So if already turbulence and splashing are the issues here, and if we are using a non-ferrous material, and that will enhance the issue rather than reducing it. So because of that, we will not be using the non-ferrous materials here. Okay, so now we'll be discussing, I think I already have mentioned about the time of filling for top gating system, right? So what is the formula? The formula is volume of mold. Somebody was asking in the last class, what is VM? VM is nothing but volume of the mold cavity. So here it is, I mean, I've taken it like this. If you see here, okay, let me take the pointer. So if you see, this is the height of the mold cavity, and this is the area of the cross section of the mold cavity. So then volume of mold cavity will be height into area of the cross section, right? That is VM. VM divided by H into Vg. No need to worry about this derivation. If you want to, you can just go through it. It's very easy to understand. But yet, for the sake of this examination, I request you to try to remember this formula. Okay. It's, I mean, of course, if you see the derivation, it's very easy to remember. But anyways, as we don't have much time here, I request you to try to remember this formula. That is, time of filling for top gating system is equal to volume of the mold divided by the area of ingate. Okay, area of ingate. Where is ingate? Ingate is the point at which the liquid metal is entering into the mold cavity. Okay, so this area, the bottom of sprue area, if at all you are considering it to be a top gating system. Okay, so this is the area of ingate. Okay, area of ingate, cross sectional area of ingate into velocity at this point, velocity at this point. Okay, velocity at this point. So already we have said that the velocity of gate ingate is equal to under root 2g ht, where ht is total height, that is height of the cup plus height of the sprue. Height of the cup in the sense height of the pouring cup or pouring basin plus height of the sprue itself. So hc plus hs is equal to ht. Okay, so this is where we have stopped in the previous class. Let's continue from there. Okay, so now we'll discuss about bottom gating. Yesterday I also told you where we have taken a tap and directly we are filling the bucket from top, and also we have taken a pipe connected to the tap, and then we have connected that another end of the pipe to the bottom of the bucket. So the water is filling from the bottom. That same thing has been drawn in the terms of casting. Okay, so if you see, this is the height of the cup and this is height of the sprue. Rather putting the mold cavity at the bottom of the sprue, you're directly connecting this bottom of the sprue to the bottom of your mold cavity. So this is your mold cavity now. Okay, this is your mold cavity, and AM is the area of cross section of your mold cavity, and HM is the height of your mold cavity. Okay, and this is your riser. Okay, this is your riser. Okay. So now ingate is this. It's not this. Okay, ingate is this. Why? Ingate, we have already discussed the definition. That is the entry point of liquid metal into the mold cavity. Yes, yes. So now from here it will keep on entering and it will go from bottom to top. Okay, time of the filling will be from bottom to top. Okay, fine. So the points what I have mentioned in the previous slide on the top gating will be quite opposite. These are 5 points. Quite opposite to these 5 points will be these points. Like here, liquid metal enters the cavity from bottom and it will move upwards. Velocity of liquid metal is neglected. Why? Because here the velocity is coming and it is trying to go from here. So obviously, instead of falling from here, it is not dropping here. There is no other gravity here. That directly it is coming and it is taking this path, and it is almost negligible. Why? Liquid metal in the sense this one. top of the liquid mid, not this. At this point, liquid, obviously there will be, obviously here at this point there will be velocity. It's not that there is no velocity here. What I'm saying is that the velocity on at the top of this thing, okay, velocity at the top of this thing, okay. So here also what velocity is that this thing, velocity at the top of this layer when it is filling as the thing is moving up, okay. So that is what they are saying, okay, fine. So, and there is no possibility of turbulence splashing. Obviously it is quite intuitive here. I mean, we can see it clearly that there is no splashing occurring because it is filling from the bottom, and it is used for non-ferrous materials, obviously, because here we told that there is no, we can't use non-ferrous material. So where can we use? We can use it here, okay. So this bottom gating is used for casting the non-ferrous material, okay? And there is unfavorable temperature, because why unfavorable temperature gradient? Because first liquid will fill here, and then after some time what will happen? The liquid will try to, what you say, they will try to get solidify. Again some metal will come and that solidify will move up. So that temperature gradients is not properly formed here. Because of that, unfavorable temperature gradients will be formed. Okay, that is the reason why non-uniform solidification is happening in this case. Okay, so this is what I'm getting. And here also we should be able to identify what is the time of filling of this, because obviously if you're filling from the top, right, if you're filling from the top side, the filling time will be different. If you're filling from the bottom, the filling time will be obviously different, right? It is traveling through the runner and all. So the formula for that is this. The formula for that is this. This is, forget about all this derivation. The formula for that is, this is very big. I hope you remember this formula for the sake of this examination, but they might not ask, or they might ask, I don't know, maybe with some easy values in the sense of simple values they might be introducing. Maybe this value is 10 and this value is some 5, something like that. They'll be introducing some easy values where you can calculate it easily with hand. No need to use any calculator. Okay, so you have to remember this formula. That was very easy. What was the formula? That is Vm by what? You remember that formula for top gating? Yes, I'll write it here. The formula was TFT, time of filling for top gating, is equal to volume of the mold, that is AM into HM, divided by AG into VG. VG is nothing but 2G HT. HT is HS plus HC. Okay, we had this formula. And bottom filling, we have this formula. Big formula, but I think there is no other way out. You have to remember this. This is 2 by under root 2G. And this, if you want to cancel, and you can write like this also. Under root, like this also you can write if you want. If you want to write, you can write like this also. Okay. So if either you can write it 2 by under root 2G, or you can write under root 2G, 2 by G. You can write whatever you want. But anyways, this is the formula. So okay, this is AM by AG, area of the mold, cross section of the mold, divided by area of the ingate. Now what is the area of ingate? Area of ingate is this. Area is this area. This is the area of ingate. This is the area of ingate. Initially this was the area of ingate for top gating. This for bottom gating, this will be the area of ingate. Okay, fine. Next is under root HT. HT is nothing but what? HS plus HC, height of the sprue plus height of the pouring cup. And HM is mold height, mold cavity height. Mold cavity height is this. Mold cavity height is this. Mold height is this. So somehow you have to write this formula in your short notes, and I think you should be able to remember that formula. Okay, remember this formula. Okay, and this is for bottom gating. Bottom gating. Okay. Now there is a special case. What is a special case? It's nothing but, what if your height of the total height, that is HT, is equal to total mold height. HT is equal to HM. In the sense, if you see here, what I mean to say is that if your total height, this is your sprue, it is your what is the HC, and this is HS, and you're trying to fill it, and this is your total mold, and let's say this is HM. Okay, if HC plus HS, what is HC plus HS? That is HT. If HT and is equal to HM, obviously these both are equal, right? Both are at same things, both are equal, right? If these two are equal, then what happens? It boils down to this formula. What is this formula? That is time of filling for bottom gating system is equal to 2 times the filling of top gating system. It's very important formula, and this can be asked in your HL exam as well. How? Because he'll simply ask this thing. If at all the total height, or maybe he says that the summation of sprue height plus pouring basin height is equal to mold height, they say. That's what they'll give in the question, and they say that which of the following is true. They may write like TFB is equal to TFT. TFB is equal to 2 times TFT. TFB is equal to 3 times TFT. TFB is equal to 4 times TFT. Anything can be asked. Okay. Or sometimes they might be giving some numericals, and we have to substitute that numerical values and find out whatever the unknown that the person is, that examiner is asking. Okay. So time of filling of bottom gate will be equal to 2 times the filling of top gate if HM is equal to HT. So every derivation is there. So all this thing is derivation. I'm not going through derivation. You can it's very self-explanatory if you're going through the derivation, but I'm not going through that because it's not a complete gate class, it's a revision class, and there's no point in discussing that. Okay, you have to know the end result, and that's what is important for now. Okay. Okay. So you write this formula also in your shortcuts. If HM is equal to HT, then time of filling for bottom gating system is equal to twice the time of filling of top gating. Okay, fine. Let's move on. Now, so there is obviously some question has been given here. What did they ask in a gating system? Dimensions have been given. So this is your dimensions of your casting. Okay, this is your dimensions of your cavity or casting, whatever it is. Okay, mold cavity, mold cavity, mold cavity. Okay. Now, height of the liquid gate, height of the liquid metal above the gate, height of the liquid above the gate. What does that mean? What does it mean? Height of the liquid above the gate is 15 centimeters. What does it mean? Anyone? What does this sentence mean? What does the sentence mean? Anyone? So let me draw the dimensions. They said 50 cross 25 is bottom. This is, let's say, 50, and this is 25. And mold height is maybe this much. How much is this? Maybe the mold height is 15 centimeters. And they are saying that 15 centimeters liquid, the height of the liquid above the, okay, there's some answer, I think. Yeah. Yes, it is HT, Prabhakar, you are right. This is HT. Why it is HT? Why it is HT? Liquid height of the liquid metal above the gate. Because let's say if you are considering it to be a top gating, above gate liquid metal starts at this point, and from here the liquid metal is coming, right? So this is 15. If you are considering top, bottom gate also liquid metal is starting here, so obviously this will be 15. So in any case, in question what is given is HT. Okay, and cross sectional area of gate, that is what, this is what, AG, area of gate. Now they are saying determine time required to fill the casting using top gating system and bottom gating system. Okay, so what is the formula for top gating system? Formula for top gating system is TFT is equal to volume of mold divided by area of cross section of mold into, sorry, area of in gate into volume at the in gate, sorry, area of the gate. These are two gates. So what is the volume of the mold? This is AM, this is AM, and this is HM. So it is total volume AM into HM, that is 50 into 25 into 25. Let it be in centimeter itself. So we have to substitute everything in centimeters. Remember that. Please remember, units are very important in the examination. Here he has given clearly that centimeter. So we are substituting in centimeter in the numerator. Of course, we have to substitute everything in centimeters in the denominator as well. Okay. So area of gate is already given, that is 5 centimeters square. Okay, and Vg is under root 2g ht. You know, this is ht, this is ht, right? 2g ht, 2 into g. G is 9.81 meter per second square, right? If you want to convert this into centimeters, right, it will be 981. You have to remember that. Okay, this is 981 centimeter second square. Okay, so 2 into 981 into height is how much? 15. Then if you substitute all these values, you will get some value TFT. You're not doing that. There is a solution, don't worry, I'll show you that. Now once you get TFT, after that you have to calculate TFB. So for TFB, we have seen a very big formula. Should I substitute that formula? Is there any other shortcut for doing this question? Anyone who can give me a hint? How can I do this TFT? Should I use that big formula? Yes or no? Yes. Why it is twice, Praveen? Can you say why it is twice? Why it is twice? Why TFT is 2 into, okay, Naveen also told why it is TFT 2 into TFT. Why I am asking? Yes, because HT and HM both are same. Obviously, you can easily calculate. Once you get TFT, you can substitute TFT here and you get 2. So you have saved lots and lots of time, right? If this kind of a question is given gate also, it will be easily solved, right? Because no need to be, sometimes people don't observe that HT is equal to HM. They'll put a big formula and they'll waste their time. Of course, they'll get right answer, but there's no point in substituting, right? That's the thing. Fine. So fine. So this is the solution. This is the solution for that, obviously. So obviously we see you have substituted as centimeters 991 centimeters and 21.86 seconds, and then as this is thing, and that is 43.72 seconds is the answer for this question. Okay. Okay, fine. Now parting line gate. What is parting line gate? It's nothing but the gate is connected in between. I told you already, in between at the parting line, and some of the liquid is for the portion A. For the portion A, top gating system will be followed because it is the liquid is falling from the top. For the portion B, it is following the bottom gating system. Okay, that's it. And generally people use this kind of system very often. Okay, very often they'll be using this kind of a system where the gating system is in both mixed. That is, the in gate is put near the parting line. Okay, very commonly used. Fine. Now step gating, obviously that is the fourth gating, and here we have steps. So first initially here it will fill the bottom, and then it will fill the bottom, and then it will fill the bottom, and then it will fill the bottom like this. It will keep on filling it. Okay, so like this, mostly people will try to reduce the turbulence and all these things by step gating system. Okay, okay, 1 minute, last slide. Okay, is it okay, Naveen? Did you see this? Okay, no need to take any snapshots, anything like that. I'll be providing all these slides. Just listen to them. If you want anything as immediately, okay, it's fine, but no need to write down anything. I'll be providing the slides. Okay. Yeah. Okay, done. So fine. So next. Okay, next is this thing. So now fluidity is very important, because if your fluidity is not very high, let's take water. Let's take water. Okay, or maybe we'll take maybe some kind of very viscous fluid. We'll take maybe some high viscous fluid like what should I say? Some kind of juice. Okay, juice, some fruit juice which is having good viscosity, like mango juice. Let's say mango juice. Okay. So now you are pouring into this like this. So obviously, who will flow fast? Water will flow fast than mango juice, right? Because viscosity is a little higher than water. So, and that viscosity and all this density of all this liquid metal will depend upon its fluidity. That fluidity will depend upon its temperature, right? How much heat you are providing to that. If you are putting less heat, then the fluidity will be very less. If you are having a good heat, then fluidity will be very high. So fluidity is also very important, because it should not come and it should not fill half and then it should not get solidified. So why we are calculating all this time of filling? Because your liquid metal will get solidified very fast. So within that time you should be able to fill it. Then in that way only you have to design all these gating elements. Okay. So this is done by spiral test. What is spiral test? It's nothing but you have some kind of a spiral like this, and you will pour liquid metal, and you keep on pouring it, and suddenly it will stop solidifying it. And suddenly it will get solidified at this point. Then you will calculate the length of the spiral, and you say that okay, this is my more the length, more the fluidity, less the length, less the fluidity. That is what is the fluidity spiral test. So they might ask this question: which of the following test is used for calculating the fluidity or finding out the fluidity? Then you should be able to say easily it is spiral test. Okay. Next, choke area. Now, to remember this formula, there's a very big formula. Please remember, choke area is nothing but the minimum cross section area in all the gating elements. the minimum cross section area in all the gating elements. So it might be at the end of sprue, or it might be the runner cross section, or it might be the in-gate cross section, because here we've seen if it for top gate this was area of gate. So here we have area of sprue, area of down sprue cross section. This is area of runner cross section. This is area of in-gate cross section. Okay, in-gate AG, in-gate cross section. Okay, now whichever is minimum out of all these three areas, and that is called, let's say if area of sprue is minimum of all of this, then this is called choke area. Let's say if area of gate is minimum of all of this, then this is called choke area. Choke area is nothing but where the area is very less. That's it. That is what is called choke, the place where choking is happening. Okay, fine. So now based on this choke area, there is another thing that we have to, there are two categories that we have to remember, that is pressurized gating system and unpressurized gating system and pressurized gating system. Okay, so if you see, this is unpressurized gating system and this is pressurized gating system. Okay, so why it is called unpressurized? It's nothing but the choke area, if let's say the minimum cross section of all of the complete gating system is having at this point, let's say at this point the minimum cross section is happening, then obviously this is called unpressurized, because your choke area is less here. Slowly by the time it is coming here, you won't have much of pressure at this point. You'll have with little pressure, this will come here. So that's the reason why this is unpressurized. This is called unpressurized, because you have to see where the liquid is entering into the mold cavity. That is very important. Okay, so if your area of cross section of down sprue is the choke area, then it is called unpressurized area. So this can also be a question. Okay, so then, and before that you should be able to understand what is gating ratio. This GR is called gating ratio. Okay, gating ratio is nothing but area of down sprue is to area of runner is to area of in-gate, right? That is what area of cross section of down sprue is to area of runner is to area of in-gate. Okay, so now if you see, obviously in these ratios, down sprue areas are less. If you see, these down sprue areas are less compared to all the other two areas. So this is area of sprue, this is area of runner, and this is area of in-gate. So in all these ratios, if you see the first one is less, it means that the area of cross section of down sprue is less, which indicates that this is unpressurized system. If you see this kind of ratio, then this is unpressurized system. Okay, so why we are using this unpressurized system? See, there are these reasons. There won't be any possibility of turbulence, and there is no possibility. There is a possibility of aspiration effect. So in unpressurized, what is the problem? As the pressure is choked here, it might happen that if you are doing Bernoulli's, if you are applying Bernoulli's equation, continuity equation between these 3 points like this, as the area is very less here, there might be a possibility of negative pressure again created here. So there might be a possibility of aspiration effect if you are not taking care of the sprue design properly. But yet you can avoid it by using some other techniques. Okay, and casting yield also. I already told you, casting yield means total volume of the casting and total volume that you are trying to pour into the liquid metal. Obviously, volume of the casting plus the gating elements that is getting freezed on. Okay, so here the casting yield also will be less. Okay, next, it's quite opposite here. It is quite opposite to the unpressurized system, and this is pressurized system. The pressurized system is having the choke area at in-gate itself. So if you are, the choke area is at in-gate, then this is called pressurized system. Okay, and if you see again the gating ratio values, the area of in-gate are having less values compared to other two values in the ratio. Okay, and this is called unpressurized system. No, sorry, pressurized system. Sorry, this is called pressurized system. Okay, fine. Now, and if you see this kind of a gating ratio, you get confused, because sir, this area and this area are small, so both are equal and small. So now which gating system is this? And of course, this is pressurized, because every time you have to take care the point at which the liquid metal is entering into the cavity. So obviously, in-gate is the place where the liquid metal is entering into the the liquid material is entering into the mold cavity. So obviously this will be your concentration. So if both are matching here, your concentration should be at the ingate, hence ingate is less, hence pressurized system. Okay. Why there is a difference in casting yield? Okay, so fine, I'll tell you here. So here, if it is unpressurized, this is unpressurized, right? So obviously here the pressure will be low. It means that the liquid will be falling with very low velocity, or maybe with low, pressure is less, so it will be falling with little less velocity and all like this. So because of that, the what you say, uh, it's not about velocity. Sorry, it's not about velocity. If you are having air aspiration effect, yeah. So if the choke area is less here, there might be possibility of air aspiration effect. So you should be able to provide a little more extra care in the gating elements. So as the gating elements are keeping on increasing, your casting, obviously, if your volume of gating elements are increasing, it means that the casting heat will be coming down. So because to avoid this kind of air aspiration effects, all these things, it might happen that it's not sure, you'll be using more and more gating elements, gating element volumes. Okay. And also, as it is falling, the riser volume also might keeping on increasing, because the shrinkage, or maybe the filling is not properly done. So there are so many reasons behind it. I'm not damn sure about the reasons exactly why is this. One possible reason could be this, because the air aspiration effect, you have to produce good amount and right amount of gating volumes. Okay, that is the reason why the casting yield is less in this case, and obviously it is reverse in this case. Is it okay? Okay. So the answer, frankly speaking, the answer what I told is not an exact answer. To be frank, I am also not sure. Let me check and come back to you tomorrow. I'll let you know what is the answer. Okay. Okay. Fine. So next, we have seen the gating ratio, all these things, and this kind of gating ratio doesn't exist. Why? So if your runner ratio, area of cross section is less, it means that your system will be like this. Runner area of cross section is less. Runner area of cross section is less. It's like this. So if runner throat is happening here, liquid metal will come and it will destroy the sand particles here. So that's the reason why there is a possibility of erosion. And because of that, this kind of gating ratio, where runner area of cross section or choke area at the runner cross section is not allowed. Okay? Doesn't exist. It's not used in practice. Okay? Fine. So now, if you see, there is a question here. Anyways, I'm not going to solve it. So just they're given this kind of system. So which kind of a system is this? Anyone? Which kind of a system is this? Is it a pressurized system or unpressurized system? Anyone? Who can say this? By seeing this gating ratio, what is this? Yes, this is an unpressurized. Why? Your your area of cross section of down screw is less. Obviously, it is unpressurized. If this is less, then this is pressurized. Okay. So obviously, then this is unpressurized system, and then you have so many formulas. You have to calculate choke area and all the things. You can just scan through the solution once you get the slides. I'm not solving it. Okay. Next. Next. Next is solidification time. Okay. What is solidification time? I told you already. First thing is that you have to pour it properly with a limited amount of time. Time of filling for top gating system, bottom gating system. We have found out. We have calculated all of this thing. Now we should be able to estimate how much time it is going to take to solidify completely. That is very important, right? So that goes by this principle called Chvorinov principle. Swarinos Principle says that your time of solidification is directly proportional to volume by surface area whole square. And please, I am telling this is square, this is square, this is square. I'm telling you, people will forget this factor in examination in hurry. They'll just simply write that Ts is equal to K into V by SA. Or they'll write the formula square, but while calculating, they'll forget to square that up. Then they'll end up in wrong answer. And I have seen so many people, so many students making this mistake. Even though I'm telling it again and again, people will make mistake. I'm telling you again, please don't make this mistake. The mistake that you are going to make is nothing but you will forget the square. Sometimes you write the formula v by sa whole square, you'll write and you'll say that that is 4 by some 2 whole square, you'll write, but you'll write 2 is the answer. 2 square is the answer, that is 4. You'll write 2. You'll forget. In hurry, you'll forget. That happens everywhere. Don't make that mistake. Okay. So now taking this proportionality out, you can write this k as your solidification factor. So hence the formula has become like this. That is solidification time is equal to solidification factor into volume of the casting divided by the surface area of the casting whole square. Okay. Why it is like this? Volume denotes the storage of heat and surface area denotes the capacity to transfer the heat. Both are opposite. Volume says I want to store it. Surface area says I want to release it. Obviously, if your surface area is more, it means that your heat is releasing very fast. It means that within less amount of time, your time is less. Within less amount of time, your thing is getting solidified. Your casting is getting solidified. Let's say if volume is more, a volume will say that I want to store more. If your volume heat is more, it means that it will take more time to solidify. Right? That's the reason why obviously this directly proportional and inversely proportional are justified here. Okay? And square is very important because that rate at which it is happening is taken into the square. Okay? So this is the formula that you have to remember. That is Ts is equal to K into volume of the casting divided by the surface area of the casting. Volume of the mold cavity divided by the surface of mold cavity, whatever it is. Whole square, whole square, whole square, whole square, very important. Okay. Next. Okay, this and all you can do. For a simple cube, volume is A cube, surface area 6A square, total V by SA is E by 6. This is P by 6 for a sphere. For a cylinder is this. It's nothing, simple geometry. For the sake of easy understanding or for the sake of simple geometries, I have done this. You can just scan through the slides when I am providing it, and if you want, you can do this kind of thing in examination also. There's no big deal to remember these things. It's very simple. Okay. Simply I have taken some simple geometries and then I have calculated the volume of the geometry divided by the surface area of the geometry. I hope you understand this thing, right? Fine. Next. So let's solve this question. I won't. Yeah. Let's not solve exactly. We have the solution here. We'll solve our practice questions. So what is this question? Let's see. A molten drop of liquid metal which is spherical in form with radius 2 mm, right? So they say that there's a molten liquid drop in a spherical form, which is sphere, and they're saying that the radius is 2 mm. Fine, okay. Will solidify in 10 seconds. So this solidification time for this spherical drop, molten drop, liquid drop is 10 seconds. In 10 seconds, it will get solidified from liquid to solid. And what is the solidification time of some metal molten drop which is double in radius? They are saying that there is another case. This is, let's say this is case 1. Case 1. There is another case where if your molten liquid drop is double in the sense what? If it is 4 mm. They are saying that what will be my solidification time? Okay. Anyone who will do this? Can try this? Anyone? Can anyone answer this question? We have already seen the formula, that is Ts is equal to K into V by SA whole square. Anyone? Prabhakar has 20. What about others? What about others? Okay, let me solve. Prabhakar, I know where you made mistake. I'll tell you where you made mistake. You see, it's okay. This is 10 seconds. This is this thing. And you have used this formula. And you have divided case 1 by case 2. And you did all these calculations. I'm damn sure you forgot this. That's why your answer is 20. You didn't you didn't use that square. That's why you have given your answer as 20 seconds. Answer is 40 seconds. That's what I told you. People tend to forget that. It is by intuition you feel that what I'm doing is right, but if you think, come back, you step little back and just think it, then you'll understand. Okay, fine. This is a square and you square it up, and that is the answer, right? This is the answer. Okay? That is the answer. So answer is 40 seconds. Okay, answer is 40 seconds. If you just, this is 2, right, 2 and the answer is 10, right? This is 10 seconds, and we had 4, right? And then PS2 is equal to 10 seconds. How much they are asking? Yes. Okay. Okay. You got clear? Then it's okay. Okay. So, and same thing here, they have given 7, 8 times heavier. They are saying, instead of writing here, they doubled the radius. Here they are saying the cubical casting will solidify in 5 minutes. So there's a cubical casting and it will solidify in 5 minutes. The solidification time is in 5 minutes. Let's say, what is solidification of same cubical casting if it is 8 times heavier? So this is case 1. In case 2, they are saying that this cube, let's say if this is having mass m, they're saying that m2 is 8 times m1. If this is the case, what is TS2? They're asking. So what is nothing but you have to do some calculations like m2 is nothing but rho 2 into v2. Okay, so we can say here that, okay, let me write that. So if you see this mass, we can write as rho 2 into v2, density into volume, that is 8 into density rho 1 into v1, and they are saying that it is same cubical casting, same material, so rho 1 and rho 2 are same, cancel them, v2 is equal to 8 v1, and they are saying that both are cubical itself, both are same cubicals. So a2 cube is the volume of second casting, it is equal to a1 cube will be the volume of first casting. So if you take this here, then a2 will be cube root of a1 cube, and that will be a2 is equal to 2a1. Once you found out this relation, obviously ts1 by ts2 is equal to v by sa of 1 whole square divided by v by sa of 2 whole square. You do all these things and then you find out ts2. That's it. So I'll show you the solution. Okay. So this is the solution. So first you calculate this, then you do this. You'll get the answer as 20 minutes. Okay. So fine. The solution is already here. Just check it out. Okay. And then there is another question. It is a little extended version of some previous questions. And this is the solution. You can check it out. Okay. Next. So now let's design the riser. What is riser? Riser is nothing but, I told you already, it is compensating 2 shrinkages. What is that shrinkages that riser is compensating? If you remember, in the first class we have discussed. Anyone? Why riser is used? Hello? Guys? Why riser is used? We have already seen that in the previous class. Guys? To compensate what? To compensate shrinkage. Which shrinkages? Yes, to compensate shrinkages of AB and BC. There is a name for AB and BC. A to B and B to C and C to D. We have written that clearly. We are in that temperature versus time profile. We have seen that this is A, B, C and D. So A to B and B to C. What are that? Liquid shrinkage and solidification shrinkage. Excellent, Naveen. Yes, you're right. Liquid shrinkage and solidification shrinkages are compensated by riser. Now, who should solidify first? Obviously, you're providing this shrinkage. The shrinkage is happening with the casting. Casting is shrinking. Casting or the metal that you have poured is getting shrinking. And you're providing riser for that. Okay. Who should solidify first? Casting should solidify first or riser should solidify first? Who should? No, if riser is solidifying first, then casting. Naveen, you should think this logic. Let's say if riser is solidifying first, Because what is the purpose of riser? It is providing some liquid. It should provide some liquid where there is liquid or solidification shrinkage, right? If at all, if riser is solidifying first, then casting is shrinking, then who will provide the liquid? Got it? Yes. So casting should solidify first, then only riser should solidify. Okay. So you should design riser in such a way that casting solidification time should be, casting solidification time should be less than riser solidification time. Riser solidification time should be always more. It should take more time to get solidified. Casting solidification should be less. Then only after this solidifying, riser can, if they'll see some shrinkage, and riser can happily provide that liquid. Okay, please do remember that. Okay. Now, so then you have to design that riser in such a way that your riser should be, solidifying as slow as possible. So that is what this point is. Rate of solidification of riser should be less than the casting. This is the point. Okay. And here we will define one more term, that is cooling characteristic. Cooling characteristic is nothing but surface area by volume. We've already seen that volume by surface area. Where did we see? In the solidification time, whole square K is equal to solidification time. Cooling characteristic is given by surface area by volume. So surface area, I already told you, it represents heat transfer. I want to transfer as much as possible. I want to release the heat as much as possible because of my surface area. I got more surface area. It means that I have good amount of space to release heat. Volume says I want to save the heat, in the sense heat storage. Okay. So heat transfer is more in numerator. Heat storage is in the denominator. Now, if you see, I told you already, solidification time of casting should be less than solidification time of riser. So here V by SA is there in this case, but here S by VA is there. So cooling characteristic, that is S by SA by V of casting, should be more than SA by V of riser. Is it making sense? Yes or no? Is it making sense? Why I have written this? Yes. Yes. So why? Because if surface area of casting is more, this will fastly cool. It will solidify very fast. Then only riser will solidify. Okay, fine. So these are the important points. Now riser can be of, so so riser should be in such a way that your surface area should be as less as possible. If your surface area is less, then it leads to less heat transfer. Then it leads to more solidification time, right? Less heat transfer, so much amount of heat is there, so it will slowly dissipate. So much time it will take for the riser to solidify, right? So if you see geometry wise, spherical riser or spherical geometry will have as less as surface area, because of, you see, the nature tendency also, if we're trying to drop some liquid, liquid from some height, some drop, so automatically as it is coming down, because of the surface tension, all these things, it will form into minimal surface area, that is sphere, right? So you can't use this sphere as riser, because if you're putting riser like this sphere and you're putting your cavity, this is your cavity like this. So there is a very small point where the riser will give you the thing, and also the solidification solidification front will be like this. Solidification front will be like this. So let's say if this complete thing has been solidified like this, and red hot metal is in between. Red hot metal is in between. It is in between, but how it is going to come and get into this cavity? It can't get into that. So that is the reason why spherical riser is not used, even though it is having minimal surface area. Okay? The next two options are parallelepiped and cylinder. Okay? So you can use parallelepiped or cylinder as your riser elements, geometry wise. Okay. Next. So in that we have two risers, that is side riser and top riser. Side in the sense you are putting it anywhere at the side of your casting. Top is exactly the top. Till now we have seen top riser, like when we are drawing this liquid metal, sorry. Okay. So when we are drawing all these things, so when we are drawing all the things, I have drawn your riser is top riser, right? So it's not like that. We can even draw the riser like this also, side riser. So we can put side or we can put top as well. Okay. So that is very important. If you are putting top, this bottom part will not be considered as your surface area because it is connected to surface area. Is what? Surface area is the area at which the heat transfer is happening. So if you see, the heat transfer is happening at these points only. Okay. So that is the reason why pi d h plus pi by 4 d square. Pi by 4 is d square is the top one. But in this case, full total is your heat transfer area. So surface area will be pi d h plus 2 into by 2 top one and bottom one. Here bottom is not contributing to any heat transfer because it is directly connected to the casting. Okay, that is the important point that you have to take care of. Okay, and then in the two things there are some conditions. I'll go to the these are the conditions. These are the optimum conditions for side riser. For side riser, if that is a cylinder, these two are for cylinder. Okay, for parallelepiped there will be another thing. Okay, cylinder. For side riser, for optimal riser, h should be is equal to d, and for top riser, h should be is equal to d by 2. Because for cylinder you need to have two parameters. One is height, another is diameter of your cylinder. So for side riser, if you are selecting as a side riser, for optimal the riser, h should be equal to d. For top riser, h should be equal to d by 2. You have to remember this. You have to remember this at any cost. Write this thing in your short notes. If you want to see the derivation, why we have lead to this kind of thing, you can see the derivation as well when I'm providing the sides. The volume went down a little. Now, Praveen, is it with Praveen or with everyone? Volume. My volume is fine. Okay. Praveen, I think please check your internet connection. Okay. Okay, fine, no problem. Carry on. Fine. So this is what the side riser and top risers are designed for cylinder. Okay. And now we'll do some riser design and then we'll do some problems. Okay. So volume of the riser can be 3 times the shrinkage of the volume of the casting. Because why? Volume of the riser, what you are designing, you can't expect like, okay, my shrinkage is happening some some 20 centimeter cube of volume of shrinkage is happening, then I'll provide exactly the same volume to the riser. No, you can't do that. You can take some factor. The factor is 3 here. 3 times the shrinkage of volume of the casting. Let's say if the shrinkage is happening 60 centimeter cube of volume of shrinkage is happening with the casting. So then what you do, you put the volume of riser as 60 so that some extra need is there, it will be taken care of. Okay. So that is what is one simple way, 3 times the shrinkage volume of casting, that can be the volume of riser. Okay. And another thing is, okay, let's use this. This thing is this, that is freezing ratio. This is very important. Okay. The formula here is x is equal to a by y minus b less c. Okay. Here x is nothing but freezing ratio. Freezing ratio is defined like this: cooling characteristic of casting, that is SA by V of casting, divided by cooling characteristic of riser, that is SA by V of riser. Surface area of riser, surface area of casting divided by volume of casting, total divided by surface area of riser divided by surface area of volume of riser. Obviously, in the previous slide, we have seen that surface area of casting should be greater than surface area of so cooling characteristic of casting should be greater than cooling characteristic of riser. So obviously here this is greater than 1, and that is given as freezing ratio, and that freezing ratio is given this x coordinate. So this x is nothing but freezing ratio. Okay. Freezing ratio is equal to a is some constant, y is nothing but this thing, that is volume of riser divided by the volume of casting, and b minus b and plus c. This a, b, c are some constants. They depend upon material, whatever it is. Okay. Now, why is this? X is freezing ratio, the big formula, SA by VA, all these things. If you take some different materials and different surface areas and volumes of rises and castings, if you're plotting all the points, then this will be curve. This will be the curve that is being formed. And your design should be in such a way that you take your freezing ratio and you take your surface area by this volume of riser by casting. This point should be here on the right hand side of your curve. On the right hand side of your curve. Then only the casting that you're trying to form will be good. Okay. And if you're taking the point below this curve, then it will be poor casting. So how can you use this, sir? Of course, we are designing riser. How can you use this? How do I use this, sir? What do you want to find? You want to find out this riser thing, volume of the riser. The main motto is your volume of the riser. Okay. So take some point here. Then you just project, and then this point has there. Then you can find volume, and this point is there. Then you can find the surface. Already volume is there. Volume of riser is there, and from here you can find out the surface area of the riser. So then by then you will be getting this thing. Okay. So obviously when you're doing something, your point should be in this region, and then if it is in this region, then it is not a good casting, because the shrinkage that is being formed in the casting is not compensated by the riser. Okay. This is called Kane's method. This is the formula. X is equal to A by Y minus B plus C. Not Y plus, Y minus. Very important. This is freezing ratio, volume of riser by volume of casting. Volume of riser by volume of surface area by, Y is surface area of riser divided by the volume of the riser. Okay, fine. Now, let's go ahead. Okay, this is what you read. Okay, next is shape factor, naval research laboratory method. So here we have used freezing ratio. Here we will use shape factor, because here in the x-axis we have used freezing ratio. Instead of that, we are using shape factor. Y-axis is same in this both cases. Y-axis is volume of riser divided by the volume of the casting. Here, shape factor is given by length plus width by thickness of your casting. Length plus width by thickness of your casting. Okay. So these are the different shape factors for simple geometries, cube, sphere, slab, cylinder. All the shape factors are given here. Then here also again same curve will be formed, and here above this curve it is a good casting, below this curve it is a bad casting. Bad because the shrinkages whatever that are happening are not compensated by the riser. Okay. Some defective castings are being formed here. Not poor you can say, defective also you can say. Okay. Next. Last method is nothing but modulus. So there are some confusions. We should clear it up here. We know that solidification time is equal to A into V by SA whole square. Okay, fine. Then we have decided that cooling characteristic as surface area by volume. Good. Then we have discussed that freezing ratio, that is surface area by volume of casting divided by surface area of by volume of riser, and it should be always greater than 1. And again we are defining that modulus of casting as V by SA. Okay, modulus of casting is defined by modulus of something is defined by V by SA. Now in this method we are designing riser such that modulus of riser should be equal to 1.2 times of modulus of casting. It means V by SA of riser should be equal to 1.2 times of volume V by SA of casting. This is another way. The first way what? First way was nothing. Volume of riser is equal to 3 times the percentage of shrinkage volume. That is what first method. Second method is Kane's method. Kane's method, that is what is freezing ratio is equal to what you say A by Y minus B plus C. We have used this thing. Third method is nothing but we have used naval research laboratory method. There we have used shape factor. Fourth method is this. Okay, we are very important. Okay, fine. Then these are chills already. Okay, let's discuss these chills and then we'll solve some problems. Okay, so now, okay, fine. So here if you see, these are called chills. So what are chills? Okay, let me tell you. Okay, here these are the weaker sections. Why? So once you pour this kind of section, cross section is there. So this kind of a cross section, whatever this, no, this thing is there. You have poured liquid metal happily, okay, and it is getting, dissipated. Heat is getting dissipated everywhere. But if you see this section here, the heat dissipation is not very good because the surface area is not properly, there. Surface area is not there. This junctions, surface area is not there. Only one line is there. There is no surface because of that the cooling will not happen proper. Proper cooling is not happening in this weaker sections. The section 2 is weak section. Okay? Because of that, to provide extra surface area, you put some kind of a chill. This is called chill. Some external metallic object that you're putting here, so that instead of a point here, you're increasing it to a wall surface here. This is a surface now. This is a line now. This is a surface now. So surface in the sense like this is 3D. Okay, don't forget that this is a line. This is surface. It will be like this, and this will be a surface like this. Okay, this will be surface like this. You put some extra external metal, so that the cooling will happen through that external metallic object. Okay, and that are called external chills. So what is chill? At minimum cross section in mold cavities, to minimize heat transfer rate, metallic objects with high thermal conductivity. High thermal conductivity, why? It has to transfer heat as much as possible. And high melting point. Why high melting point? Because heat is getting transferred to this metal object. It should not get melted, no? So high melting point also should be there. Are provided, and these are known as chills. Okay, these are known as chills. And these are the same thing, whatever. And if the chills are external, we can provide as internal chills also. How? If you are having some, object like this, then inside, before pouring itself, I'll put some metallic objects. I'll put some metallic objects inside. And please remember, now this material of chills should be equal to the material that you are pouring. This is your pouring material, and this is your chills material. Both should be equal. Both should be equal. In this external case, this external chill material need not be equal, need not be as same as the material that you're pouring. It might be same, but need not be. But here it should be, because you're pouring, let's say you're pouring aluminum. This chills also should be aluminum. Okay, fine. Chills can be external or internal as well. Paddings. Next is whatever. Okay, paddings. Paddings are also same thing. Okay, at weaker sections, the solidification is not happening properly, so you provide this kind of paddings where heat transfer is happening properly. That's it. Okay, so this is the end of the traditional casting and their solidification time, filling time, chills, padding, chaplets, all these things we have discussed. Okay, next is miscellaneous casting techniques. Before discussing miscellaneous casting techniques, let us solve some problems. Let us solve some questions before going to the further topics, because it is too much of theory, you'll get bored. Let's discuss some problems. What happened? It's not. One minute. I'm just changing the slides. Okay. The problem with some PDF. Okay. Yeah. Tell me this answer. 21st one. What is the answer? Anyone? Okay. I got one answer, B. Let's see. Okay. 1 minute, my system is stuck. I'm not able to see my cursor. 1 minute. Why am I unable to see this? Come on, where is my cursor? Okay, I got my cursor. Okay. Okay, you're right. Answer is B. It's very simple. Obviously, in gates are the opening through which metal enters into the mold cavity. What about next one? 22nd one. Anyone? Small calculation you have to do, please do it and let me know. We'll discuss this. What about 22nd one? Okay, the system is stuck, but anyways, please do this. What is the answer for the next one? My system is stuck here. I don't know. Anyone? Hello? Okay. The system is stuck, man. What is happening here? 1 minute, huh? Okay. Alright. Can you see this cursor? Laptop just left. Can you see the cursor, guys? Okay. Then why am I'm not able to see this? Okay, I think okay, fine. So what is this? Height of the down sprue is how much? HT. HT is how much? 175 mm, right? And the cross-sectional area at the base AG is 200 mm square, fine. And the cross-sectional area of horizontal runner AR is 200 mm, okay. And no losses indicate the correct choice for the time required to fill a mold cavity of volume, assuming the correct choice for a time. So which kind of gating is this? Anyone? Which kind of gating is this? Okay. So I think we should be able to use the big formula. Okay. So what is the formula? 2 by under root 2g, right? Into what? Am by ag into under root ht minus ht minus hm. Am I right? Now do this. Now do this and let me know what is the answer. Anyone who can do this? Everything is given. One minute. The system is troubling me a lot. Do this calculation and tell me what is the answer. 2 by 2 into 10. So this kind of questions will not be asked, but anyways, let's do this. What is the area of mold? Okay, area of mold is not given. So what is given? Volume is given. Okay. So HT is not equal to HM, that also is not given. Huh? Then let's take it top getting. Let's take top getting and do this answer. It is volume of the mold divided by volume of ingot, velocity of ingot into area of ingot. Tell me this answer. What is volume? Volume is 10 to the power of 6 divided by under root 2 into 9 point, or you can say 10 meters per second into 10 to the power of 3. Why? Because you have to convert that into meters, mm, right? G you have to convert into mm into ht. What is ht? Height. Height is 175 under root into area of ingot. What was the area of ingot? That is 200. And tell me what is his answer? Anyone? Guys, what is his answer? I don't have calculator. Please tell me. What is his answer? Somebody did calculation. Is it 8.45? Everyone is agreeing with that? Are you getting this 8.45? Guys? Hello? Please do the calculation. I don't have calculator here and my system is not responding. Guys? Please tell me the answer. Calculate this and tell me. Same answer, 8.45. You're getting the same answer? Come on, guys. What about others? Okay, fine. 8.45 is the answer. Okay, correct. This is B. This is B. What about the next one? 23rd one. Come on. What is the answer? 23rd one. Answer for 23rd one. Bottom gating system is preferred over vertical gating system because, tell me. Easy, right? Obviously it is B. Good. Very good. Hope everybody, we are on the same page. I'm just moving to the next one. Okay. Fine. This one. Next one. Come on. Okay. Let's we have to see. You have to think of it. Just tell me. What about others? Somebody is saying A, somebody is saying is it D. What about others? Oh, okay. Let's let's. I need answers from everyone. Whether it is right or wrong, please. It doesn't matter. I need an answer. That's it. Think of it. Put some answer. But I need some. Don't put some ABCD randomly. Okay. Think of it. And if you think this is appropriable answer, let me know. If you're putting more answers, then I'll be able to understand how you're thinking. That is what is important, right? Okay, 1 minute, guys. I'm just having a sip of water. Okay, fine. I got some answers here. Okay, that is A, D, 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 A. Okay, answer is A. Okay. Generally, normally they are saying the cross section of all elements they consider it to be a circular one for some good reasons actually. Okay, so even the sprue, the runner, okay, and even the riser. So generally they consider this, circular systems, circular cross sections. Okay, 25th one. What is the answer for 25th one? Answer is A for 24. Yeah. Okay. The stream velocities are reduced, thus the turbulence and aspirations are minimized. Turbulence and aspiration effect are minimized. Where? I want an answer. 25th one. In both the pressurized and non-pressurized, you feel that the stream velocities are reduced and thus the turbulence and aspiration effect is minimized. What do you feel? Is it true what I'm saying? In which system turbulence is minimum? Guys, okay, I'll tell you this. Let's say if at all this is the this thing, and this is the bottom gate, whatever it is, and if your velocity is very high, okay, here the turbulence will be very high because full pressure. Okay, no bottom. What bottom, Praveen? I didn't get you. I'm asking whether it is a pressurized system or non-pressurized system. This is for 25th one, not for 26th one. Answer for 25th one I'm asking. Yes, it is non-pressurized because if the pressurized, non-pressurized, if the pressure will be non-pressurized system, the choke area will be this. This is non-pressurized. The choke area is this. Then obviously the velocity will be very less here. As the velocity is less here, obviously there won't be any turbulence. So the turbulence is minimized here. Okay. Okay. So is everyone having internet issue, guys? Am I audible? Am I okay, fine, fine. Okay, what about 26th one? What is the answer for 26th one? Come on. 26th one, easy. The gating ratio is given. Obviously, the area is less here, hence it is non-pressurized. Very good, very good, very good. What about 27th one? What about 27th one? 27th one. Please write 27 because everybody A, B, I'm not understanding. Please write 27, then answer. What is 27? Come on, guys. We have discussed this already. If A and B represents the surface area, okay, if A and B represent surface area and volume of the components under superscripts, a special measure of riser design freezing ratio R is freezing ratio. We have clearly discussed. Answer is what? Well, it is nothing but freezing ratio X. We have taken X axis, right? Freezing ratio is surface area by volume of casting divided by surface area by volume of riser. And which option is matching? Of course, option B is matching. Of course, option B is matching because surface area by volume of casting divided by surface area by volume of riser. Okay, answer is B, and this kind of questions will be asked in HL. Okay, okay, oh, sorry. A, B here, B here. Okay, next. Come on. 28th one. What is the answer for 28th one? Come on. The proper function of riser freezing ratio must be. Answer 28. Easy, no, I told you already. Clearly, I told you. That is surface area by volume of casting by surface area by volume of riser should be greater than 1. Obviously, freezing ratio should be greater than 1. Clearly, I told you it should be greater than unity. Answer is C. What about next one? 29th one. What is the answer for 29th one? Very good, sir. Very good. Very good, sir. All of them are very active, very happy. Please write. Somebody write the question number. Then obviously from there you can get the answer. Okay. What about the answer for 29 now? 29th one. Twenty-ninth one. Come on. 29th. Okay, okay. Still answers are coming up. Yes. What is that? From design point of view, ratio of minimum volume of riser to the dedicated of liquid shrinkage is kept at, simply we can do that, easy. Ratio of minimum of volume of riser to the percentage of shrinkage, liquid shrinkage is equal to, what was that we have discussed? Obviously we discussed it was 3. Why? First method, it was the first method, right? What is that? Volume of riser is equal to 3 into percentage of shrinkage. Simply is taken this percentage of shrinkage in the denominator. What is the answer? 3. Easy. Okay, very easy. Next one. Come on. Next one. 30. What is the 30? 30th one. 30. Yes, A. Excellent. Excellent. Answer is A. X is equal to A by Y minus B plus C. Amazing. Next one. 31st one. Simply you can tell this answer, man. Simply you can use this answer. What is the rule that we are using? 31st. How it is A? Guna, come on. Did we use any Bernoulli's equation? Did we use any Bernoulli's equation while designing riser? Naveen, did we use Bernoulli's equation during riser? No, we have Tejasvi. Naveen, please. Oh, Tejasvi is right. Who is A? Prakar. Why it is A? Mohammed also, who is telling A? Guna and Prabhakar are A. Why? It was Swarinos rule, right? For decision of, we didn't use any Bernoulli equation, we didn't use any current continuity equation, we didn't use any unit laws of equation. We have used Swarinos rule. What was Swarinos rule? That was surface area by, sorry, volume by surface area. Do you remember the solidification? Obviously, solidification is very important for designing riser. We have used Swarinos rule. Remember K whole square, solidification of time, all these things we have used, right? That's what we have used for this thing. Okay, again I'm not paying. Sorry for this. Other C, this was C, this was A. Good. Next one. Come on, next one. 32. Amazing. I'm very happy. All of them are writing, giving very good answers. Come on. What is the next one? 32. There will be some little calculation. Please do this calculation. Let me know. Come on. What about 32nd one? What was the formula? He's asking what? He's asking the solidification factors. K is given. This is K. Okay. K is given. And solidification time for spherical casting. He's asking solidification time Ts. Solidification time T is equal to K into volume by surface area whole square. Substitute the values. What is Ts? Ts is equal to, right? What is K? K is 10 to the power of 6 second per meter square. Okay, into volume by surface area. What is volume? Volume is for sphere 4 by 3 pi r cube. 4 by 3 into pi r cube divided by surface area. Surface area is 4 pi r square. 4 pi r square, right? This 4 gets cancelled. Pi gets cancelled. R square, R cube gets cancelled. R by 3 is left. So R by 3 whole square you can write, right? And that, what is that? What is that? So it is 10 to the power of 6 into what is R? Diameter is given. Diameter is given. Please do not forget this. Diameter is given. It is R what we are writing. R is what? 50 by 3 whole square. What is the answer now? Tell me. 33rd one. What is the answer? What is the 33rd one answer? Come on, I can't do this calculation. I think how much is this? Okay. Please do not forget. Okay, it is. Yeah. I think you here it is 10 to the power of minus 3. Okay, 10 to the power of minus 3 inside 50. Okay, because this is in meter square and 50 into 10 to the power of minus 3 whole square. Okay, this should be like this: 10 to the power of 6 into 50 into 10 to the power of minus 3 by 3 whole square. This should be the answer. Okay, answer is of course 32nd one 277.78 is the answer. Okay, 277.7. So this calculation is this. Okay, so let me erase this all the stuff, all the things you can see in the video. Anyways, answer is B. Okay, 33rd one. What is the answer for 33rd one? Third, 33 answer. Okay, Mohammed is B. Naveen is again B. What about others? It's a simple question now. What was this question? We have discussed this yesterday only. So this shrinkage, okay, this shrinkage and this shrinkage, I clearly told you. See, Praveen, how is it 5%? Hello? So I clearly told, no, Praveen, here the volume that is compensated for riser, what is the answer? Obviously, this is not the answer. Why? This is for pattern, because already it has become, what you say, solid. So 3 is not the answer. And we know that this 2, see, Praveen, you can't do that 0.98 into 0.97. Why? Because these two are in still liquid stages. No, in liquid there is no this kind of thing. Okay, in liquid you can't do that. Obviously, you can add these two. It is nothing but 1 plus 2, that is 3. So this, if already we have discussed yesterday, right? Yesterday or day before yesterday, we have discussed that clearly, that the first two are what is say liquid, and this is liquid, and this is the solidification shrinkage. These two will be compensated by riser. Yesterday we have clearly, day before yesterday we have seen clearly, first class, and this is for pattern. Okay, so answer is 1 plus 2%, that is 3%. Okay, answer is 3. Am I making my point here clear? Are you guys understanding what I'm saying here? Okay. Okay. Next one. Come on, next one. 34th one. During cooling and solidification, the pure metals and alloys have. Yes, different characteristics, obviously. Different characteristics. Good. Why? Why it is different? Why these are different? Obviously, pure metals, it is simple. Actually, it will be like this, like this, like this. Okay. But let's say if you're adding some alloy, if you're having some tin and lead, something like that, then phase diagram will be some lens kind of diagram. Okay. So that phase diagram itself will be changing. Obviously, both are having. This is unary, pure is unary. This is binary. You're adding some other thing. Obviously, these melting points of both elements are different. Because of the both elements are different, the phase diagram itself will be different. Obviously, the temperature and time curve will be different for alloys, will be different for pure metals. Obviously, answer is B. Very straightforward question. What about next one? Sorry, I'm moving this thing again and again. I don't know why. Okay, what about next one? 35th one. Come on. Thirty-fifth one. Just write 35 and tell the answer, whoever is typing first. When alloys solidify over a short range of temperatures, then they form. Oh, I didn't say this, huh? Okay. Any guess? Anyone who can guess this? I didn't say this, but anyways, I'll try to justify the answer. Okay, fine. See, please remember, I'm telling it here itself. And if you want to take a snapshot after this, you can take a snapshot. It's very important. So what is happening when you're putting this casting? This is your casting like this, and you have poured your liquid metal. Already liquid metal is inside. Let's say liquid metal is inside, and these are the walls. These are the walls of your molding sand. Okay, this is your full molding sand like this, full molding sand, and you have poured like liquid metal into this. Okay. Now, as I told you, at this wall, the temperature difference. This side of the wall, let's say it is 30 degrees centigrade on the sand. On the sand, this is all sand. And inside this thing, we have, let's say, some 1200 degrees centigrade inside. So the temperature difference is very high. Okay. So already I told you clearly in the previous class that small grains are formed on the walls because of sudden cooling. And as you keep on going inside, like this, it will form. And time proceeds, and it will increase it. And as time more proceeds, it will form this kind of columnar structures. And if time more, probably what will happen, there is some dendrites that are taking place of some other branch will take form like this. These are called dendrites, and these are called columnar structures. Columnar structure. So in this question, you have to think very carefully that what short range he told. Short range in the sense you're going till this point only. For long time only, for long time only, these dendrites are formed. Over a wide range, they say. For wide range only, these dendrites are formed. For short range, until it can reach till this columnar. If you are taking more time, then only these dendrites are formed. So hence answer is A. Yes or no, guys? Are you getting my point? Wide range in the sense more time. Let's say initially when immediately you're pouring, this short small fine grains are formed, and at t is equal to some 10 seconds, this columnar structures are formed, and at t is equal to some 20 seconds or 25 seconds, this dendrites are formed. For more time, for wide range of temperatures, this dendrites are formed. For short range temperatures, that time is not allowed, because for short range temperature means the temperature difference is very less. So easily it is getting solidified. As it is getting easily solidified, there is no much time for the dendrites to get developed. That's the reason why in short ranges only columnar is there, then it will stop there. Okay? Yes or no? Okay. So the answer is D. So A. So answer is A. Okay, next one. Come on, next one. 36th one. Come on. We have to solve all these questions. Come on. We have some 50. We have till 50 you have to solve. Thirty-sixth one. What is the answer for 36th one? Come on. It should be, answer should be coming by now. Yeah. Swarinos rule. What was Swarinos rule? Come on. It was what? Ts is directly proportional to volume by surface area whole square. So first option, what was the first option? First option is proportional to volume, square of volume. Obviously, because Ts is equal to proportional to volume square, and it is inversely proportional to SA. What is given? It is proportional to surface. Wrong, no. Both A and B, none of the answer is A. Right? Answer is A. Clear. It's very easy. 37th one. Come on. 37th one. If at all you are completing the answer, go for next one. Please don't wait for me, huh? The 37th one. Come on. Yes, answer is D. D. Somebody is saying. What about others? Tejasvi, Rishikesh. Come on, Naveen, Prabhakar. Answer is D. Amazing. You're right. Yes. Yes. It has to satisfy all these three options. Why? Of course, riser ensures directional solidification, because as it is getting solidified, you are providing. As it is getting solidified, you are providing. Okay, it will ensure directional solidification. Okay, it maintains proper temperature gradient. Because of proper temperature gradients only directional solidification is happening. Okay, next, maintain a solidification time longer than frosting time. Obviously, that is also true. Okay, so answer is D. 38th one. What is the answer for 38th one? Why it is C? I'm still not getting. Why do you want more volume? Why do you want to have more volume? The main criteria is what? Solidification of riser should be more than casting. That was important. Obviously, the solidification time of riser should be more than solidification time for casting. It is okay. But if this criteria is fulfilled, why do you want more volume? As much as less possible volume, it is enough. But it should maintain what? It should see more volume for more temperature. That's not the case. See, we are every time seeing volume by surface area. We never discussed about volume. Volume is fixed. Volume is 3 times some shrinkage volume, and we have optimized surface area, and we told that H is equal to D when it is side riser, H is equal to D by 2 when it is top riser. We have done all these things. Okay, so we are optimizing it, and we are trying to minimize. You have to take the minimal possible minimum, not minimum means minimum, possible minimum volume, but should maintain the solidification time. Answer is B. According to me, answer is B, because I can't keep so much of volume. That's waste of your what you say this thing. No, it is considering into the gating. Your casting yield will come down. Okay, what is casting yield? Casting yield is equal to volume of casting divided by volume of casting plus volume of gating elements. In gating elements only this riser will be there. If you are taking more volume of riser, then volume of gating will be increased, and total this thing will be coming down. Casting yield will be coming down. You don't want that to happen. Okay, take as minimal as possible and maintain that solidification time of riser should be more than the casting. Is it okay? Yes. Answer is B. What about 39th one? This is easy. Come on, tell me this 39th. Nobody should make mistake of this. 39. 39 easy. See, no? Is it right or wrong? Simply we have seen, already we have seen this so many times. Okay, answer is C. This Ts is equal to K into, or Ts is directly proportional to V by SA whole square. We have seen that. There is no point in writing. Okay, answer is C. This is B. This is D. And this is. Okay, fine. Next one. Come on, 40. Come on. Okay, I think you have to do some calculations here. Try it. I'll give you 2 minutes. Try it. Let's see. Actually, this kind of questions will not be asked, but for the sake of concept, maybe you can try this if possible. Let's see how many can try this. Okay, let's not waste time. I'll only do this. Just see it. Okay. So what is question? The mold has a down screw of height. What is this? What is this? 185. At least tell me this. What is this 185? Yes, HT. So HT is how much? It's 185, right? HT is equal to 185 mm. So I can write as 185 mm as what? 0.185 meters instead of 185 mm. Okay. And then the base area, that is what? volume of velocity, sorry, area of gate. Area of gate is equal to 100 mm square. 100 mm square. It can be 100 to the power of minus 6 meters square. You can write like this. Anyways, I'm converting that into meters mm. You can check that. And this is sprue. This sprue feeds the horizontal runner cross sectional area of in-gate. So in-gate area. Okay, this is not in-gate. This is not area of gate. In-gate area is this. This is the AG. Okay, and to fill the mold at cavity of volume is given here. Time required to fill the cavity. What is this? Okay, so area of gate is given, volume of mold is given, and this what you say HT is given. Then he is asking what is the time required. It is simple. What is that? TFT is equal to volume of the mold by AG into VG. You can use this formula. VG is under root 2G HT. Usually you can calculate this. And oh, okay. Here the question is little tricky. It's this AG is a tricky part here. It's not AG. It's I think it is velocity is important. Okay. Here the velocity is important. Why? Generally, what we have taken Vm by Ag into Vg. Okay. So Ag is clear. Ag is 50. That is clear. There is no point doubt in that because it in gate he has given clearly. There is no doubt in that. For Vg, we have to do some trick here. What is that? Because here we had sprue and there is some runner here. Then only it is trying to fall into this. Okay. This runner from here to here, there will be some loss in velocity. Okay, there will be some loss in velocity. That is velocity. A1 V1 is equal to A2 V2. This will be the equation that you have to use, continuity equation. So what we have calculated under root what is there? This V1 is under root 2G HT. Okay, because this is V1 and down sprue and HT is this. HT is this. But the same velocity will not be maintaining at this point. So you have to use this formula. How to use this formula? That is A1. What is A1? A1 is 100 here because here it's given 100 and here it is 50. Right? 100 into what is the velocity? That is what we have to calculate under root 2G HT, whatever is that you have to calculate here. Is equal to 50 into V2. Calculate this V2, whatever is there, and substitute this V2 here. That is what the trick you have to do here. Are you getting my point, guys? Yes or no? Guys, are you getting my point what I have said? Should I tell again? Yes. Because you can't directly substitute. Generally what you do, TFT is equal to Vm by, right, Ag into Vg. Vg is what? At the down sprue. This is down sprue. Directly you can't substitute that value because it is traveling through runner. Through runner it is traveling, so the velocity will change as the area of cross section is changing from here to here. So you have to calculate that change in velocity, and then that velocity only you have to substitute like this. So if you substituting like this, the answer will be something around. I mean, I know the option 5.24 will be the answer. Okay, 5.24 will be the answer. Okay, what about next one? What about next one? 41. Come on, please make Tejasvi, please check it again. Is it A cube? What was that? It's a very simple one, right? It's a cubical casting. A cube divided by what? 6A square, right? And then it is what? A by 6, then whole square, then A square is left, no? Not A cube. And come on, Muhammad, is it really D? How it is D? Solidification time. V by SA whole square, right? V is A cube, SA is 6A square. A by 6 will be left. solidification time is directly proportional to a square, right? A by 6 whole square, this is TS. Yes or no? Muhammad Ali has done it, right? What about Prabhakar? Are you getting my point? Answer is C. Yes. Please don't make this. See, every time you are making this mistake, please don't make this mistake. Okay? Please make sure that you are taking care of this square. Square is very important. Okay? Next one, 42. What is the answer of 42? 42. Of course, it is B. Of course, it is B. Why? Which one of the following methods are obtaining direction notification? Chills, obviously we have used it. Paddings, we have used it. In last section, just before starting this, this question and answer session, we have solved this question, right? We have solved this. I mean, we have discussed this concept. Answer is 1 and 3. Good. What about next one? Sorry, next one, 43. 43. Wantingly kept all these questions repeatedly because you don't want to make mistake and you have to not forget what we have discussed in the class. What is the 43rd question? This question we solved, isn't it? Yes or no? Did we solve this in class in the concept when we are discussing the concept? Did we discuss this? Yes or no? Answer is D, of course. Answer is D. We have discussed in class. What about next one? Next one, come on. What about answer you have to say? 44th. 44, 44. Of course. D. Simple formula. 45. Come on. 45. First class. We have discussed about this thing in the first class. 45. First or yesterday? I think yesterday's class. I think we have discussed. Chaplets. Where did we use chaplets? Do you remember? Yes or no? When we had a blind hole. Remember? We had a blind hole and then we have supported the core by using these chaplets, this I kind of sections there, and this was the core like this, right? We had supported the cores like this. Yesterday we have discussed about this chaplets, and this is your mold cavity like this, and this is your core. This is your core, right? So these are called chaplets. We have seen already clearly, right? Answer is this is 40. The answer obviously to talk about cores. And what about next one? Next one. Direction solidification. Okay. So yeah, all of the above is right answer. All of the above is right answer. Okay. According to your information, changes we are right because we have discussed only about shells. That's the reason why you have taken A as your answer. Of course, using exothermic materials is also one of the way you can get the direction stratification. I'll show you the slide. Don't worry. And increasing the certain thickness of sections also will be one of the way where you can use the direction stratification. But let me discuss next question, and then we will. I will show the slide where direction stratification. How can you attend the direction stratification? I'll show you the slide. Just tell me the answer of 47th one, and we'll close the session for today. 47th one. Obviously, there is no way you can't answer this repeated question, chills and paddings. Okay. So for directional solidification, answer is B. You're right. Answer is B. Of course, it is B. Chills and padding. Already we have solved this question here itself. Where is that? Where is that? We have solved here, not here. Yeah, here we have solved the same question, and the same question has been put here in different way. Answer is B. You're right. The directional solidification I'll show you here. Yeah, this one. So here, okay, you're putting riser and all these things. Sometimes you can put some exothermic material. That exothermic, what is exothermic? It will generate heat. It will release the heat upon some chemical reaction. Okay. So if you're releasing heat, that also is very good, because when solidification, what is solidification? Solidification means reduction in heat. Sudden reduction in heat will have some problems. So to make sure that the reduction in heat is slow in progress, we have to slow that process. We have to slow the rate at which the solidification is happening. To make that, we have to increase the heat. How do you increase the heat? Put some material which is exothermic, so that due to some chemical reaction, heat is generated. And then because of that heat generation and because of the solidification front, both are managed and directional solidification is happening. And second important thing for exothermic material is that you can put some exothermic material around the riser, so that if riser is solidifying faster than casting should be solidified fast than the riser. If riser is solidifying fast, then this exothermic material will provide some heat. Because of that heat, riser will not solidify fast than the casting. Okay, so that is the reason why we are using exothermic material for directional solidification, as well as maintaining the temperature of riser. Is it okay, guys? Hello? Okay, fine. So that's all for today. And tomorrow we will close off the casting in the first half an hour. I think I should be completed by now, but initially I took little time for you to get the grip of my teaching, pace and all. So tomorrow we'll close off the casting, and then we'll start metal cutting. And as it is, we'll be solving some good questions, and we'll proceed. Okay. Not tomorrow. I think tomorrow, is there any class tomorrow? I think my class is on Wednesday, I guess. So we'll meet on Wednesday. Okay. We'll meet on Wednesday, day after tomorrow. Any doubts, you can ask me. I'm here. Sir, one small request, can you provide all the slides before class so that we can revise for the... Sure, I'll do that. So what I'll do is that I'll share all the slides. It's not before and after. If you want, you can go ahead and read whatever is coming in the next class also. No problem for me that, because it's not some mystery, or it's not some surprise. I'll completely provide the slides. Just keep on reading whatever you want, and you attend the class, and that will be very good. It will be advanced reading, so that if some doubts are there, the class will be a doubt clearing session for you. If you are already reading in advance, that's good. That's more and good. Okay, I'll send you the slides right away today for the casting. Any other doubts? Okay, hope everybody is happy with this session. Sure, I will send all the slides. Don't worry about slides. Full material is with you, will be with you. Just only thing that you have to do is that read and practice. Read and practice. That's it. Crack it. Settle. I mean, get good marks in whatever these things. And if you're getting selected, for interview, obviously we'll help you with the interview also, and hopefully you get into the job. Okay. Anyways, so I hope the session is informative today, and tomorrow we keep. I'm thanking you guys also, because you are very active. Because of your activeness also, I am also becoming very active. So you be more responsive and active. The same way, it's like your action will relate to my reaction. So my reaction also will be very active. Thank you. Yeah.